So after giving you a brief introduction and mathematical derivation of the heterogeneous nucleation for a solid on a substrate, let me just move on to the solid. But before that, let me just tell you that this theory has been used extensively to make different type of heterogeneous nucleant for the industrial practices. To give you some example, for aluminum alloys we use titanium diboride TiB2 as a nucleating agent, and it is well proven that the aluminum nucleates nicely on these substrates. Similarly, I showed you that graphite in a cast iron or ferrosilicon in a cast iron or zirconium in others. Okay, carbon is used in magnesium alloys as one of the nucleating agents. So there are many such nucleating agents which can be actually prepared or designed using these theories. So as I said, I am going to take a few cases of solid nucleating agents, and here are the few examples. First one which I have already discussed with you, that is some beta phase forming from a parent alpha phase in such way that there is a phase precipitate already present in the alpha and on which beta actually forms. Mathematics will remain exactly same, just like one I have derived for the liquid solid. The next one is basically nucleation the gain boundaries. Okay, as you know, the gain boundaries act as a nucleating agent for the many precipitates we will see in our phase transformation discussion later part. The gain boundary actually can be considered as that. Now it is very simple compared to first one. This is much simpler than this one in the sense that what is going to happen, the phase which is forming from the parent phase alpha on the gain boundary of alpha will be forming like a double lens. Okay, this is the first lens on the top, second lens at the bottom, and at these corners the interfacial energies are balanced, but that balancing is basically for the both parallel components as well as perpendicular components. And so if you simply simply do the maths using two spherical caps, it is basically done. So how things are done, again I will be doing you the little bit maths of that, but I am not going to discuss you in details because details you need to do yourself. So suppose I have a gain boundary and I form a new solid phase as a two caps on the gain boundary. That is what you have seen in some of the pictures. I will show you later also in the actual microstructure. So therefore this is my alpha phase, this is my beta phase. Okay, and this is a pi r alpha gain boundary. So therefore this energy is basically alpha alpha. Okay, and other energy parts is basically gamma alpha beta. Okay, similarly this is also what? So this is not this one is gamma alpha beta, and these are actually angles will be of theta. Correct. So I can write down gamma alpha alpha is equal to gamma alpha beta cos theta plus gamma alpha beta cos theta. If I consider only the parallel components, so that means this is equal to twice gamma alpha beta cos theta. If I consider perpendicular components, it is very simple. Perpendicular components will be all equal, gamma alpha beta sin theta, gamma alpha beta sin theta. You can do yourself, you can actually draw that. These energy balances must be happening at this point. So now what is the delta GB equation? Delta G actually. Let us write down this is delta G for gain boundary, GB. So that's obviously again volume, and as you know volume will be double of the earlier volume which I have done. So this is very simple, twice pi by 3, that's equal to 2 minus 3 cos theta plus cos q theta multiplied by r cube. Again r is you can actually draw that R like this, so that is equal to R. Same way, I can draw a virtual sphere. Correct. So now what is the loss of energy and what is the gain of energy? Obviously loss of energy is these two interfaces created between alpha and beta, and gain is that earlier gain boundary is now recovered. The earlier gain boundary between alpha alpha is now recovered. That's the gain. So let us write down that. So this obviously will be multiplied by delta GC plus delta GV, sorry, delta GS, right? That has to be, because that's the volume, that is the energy per volume, plus the energy created because of these two interfaces, new interfaces has formed. That's again double 4 pi 1 minus cos theta r square, and this is the into multiplied by the gamma alpha beta, right? That's the interfacial energy between between alpha and beta. Basically, if you consider single lengths, this will be twice pi 1 minus cos theta r square. That's very clear. Why? If you draw this one, that's basically is equal to pi 1 minus cos theta basically. So the moment you consider that as a basically part of the sphere, then it becomes 2 pi 1 minus cos theta r square. Plus, sorry, this is the energy which is basically required. So what is the energy gain? Energy gain is because of this boundary which has got completely balanced. That's equal to pi sine square theta r square multiplied by gamma alpha alpha. Okay, that sine square is basically coming because of this angle. These angles are also theta, remember. Okay, so now we can actually do all the things. We can plug in this from this equation. We can change gamma alpha. Basically, we can make everything in terms of gain energy. So therefore, this gamma alpha beta can be replaced. The gamma alpha beta is equal to gamma alpha alpha divided by 2 cos theta, and one can simplify this equation and get something else. So what do you get? Finally, I am not going to do everything. The barrier for the gain boundary equation is again 16 pi gamma alpha alpha square divided by 3 minus delta GC plus delta GV square multiplied by 2 minus 3 cos theta plus cos q theta divided by 2. So what you can see, by making two double lengths, I reduce the barrier, or rather I increase the barrier actually compared to the complete single length systems which I shown you earlier. That is compared to the first picture on the slide, half. Okay, and so that means what? That means delta, because we are going to compare everything with in terms of homogeneous equation. That's easy. Homo, that's equal to 2 minus 3 cos theta plus cos q theta divided by 2. That's nothing but 2 f theta, because f theta is basically 2 minus 3 cos theta plus cos q theta by 4. So everything will be doubled basically. All this theta, everything I showed you, the values will be doubled here. So that is for the gain boundaries. Okay, and what will happen to the gain edges? Basically, it's very simple. One, if you look at very carefully, otherwise it will be for you. It will be look like very complex. See, gain edge is what? Gain edge means 3 gains are meeting. Here I have shown you 1, 2, 3 gains are meeting. You see here 1, 2, 2 and 3. 3 gains are meeting at this edge. So instead of 2 caps here, there will be 3 spherical caps, or 3 basically, 3 spherical caps. So you can use this concept which just now I have done for both single cap and double cap. You can extend that for the 3 cap situation and do the maths. Basically it will be again factor 3 will come into picture. What happened to the gain corner? Gain corner is again not extremely difficult. Why? because at the gain corner 4 caps are meeting. You see here there are 4 grains, 1, 2, 3, 4. So if I have 2 grains, 1 and 2, I have 2 caps, we have 3 grains, 3 caps, 4, there are 4 caps. Okay. So I can again calculate these very easily. Okay, simply multiply the areas and the volumes. Volume will be 4 times, area will be again 4 times. So you can do that. It's not very difficult task. So once you do all this maths and get this delta GB, this is for the gain boundary, delta G, basically you can get all these values. You can get delta GB star, you can get delta gain age G star and delta G corner star. 3 values for this critical barrier. And then what happen, you plot it, it will look like this. Okay. As you see here, this is heterogeneous nucleation compared to delta G star homogeneous for these 3 situations. Okay. Gain boundary, gain edge and gain corner. So as if you clearly see, gain corners are the most or the easiest nucleation sites. They are the places where the new phase will be for the new phase it is easier for it to nucleate, followed by the gain edges and gain boundaries. That is what you see in the actual practice. We always find at the gain corners more number of nucleation of the heterogeneous nucleation happens than at the gain boundaries. This precipitation based alloys, aluminum, copper, silicon, aluminum, magnesium, silicon, all these alloys, the precipitates nucleation actually governed by these aspects. Remember, this is nothing but a gamma alpha alpha by gamma alpha beta. So that means what? When the gamma alpha alpha ratio to our gamma alpha beta becomes 1.5, every nucleation is both the gain edge and gain corner nucleation is similar. And but as you decrease these values, that means when it's become 0.5, if you look at 0.5, the values are much widely different. So smaller the ratio of gamma alpha alpha by gamma alpha beta. What is the ratio tells you? That's the contact angle basically. That ratio, the gamma alpha by gamma alpha beta, there in that bow, you see on the first equation is basically 2 cos theta for the gain boundary. Okay, so that means basically it depends on the cos theta. So that ratio, if we change, if we become smaller values, then the nucleation of the gain corner is the easiest one, followed by gain edge and gain boundaries. But as this ratio becomes higher, that means the energies differences between alpha alpha gain boundary and alpha beta interfacial energy differences ratios are very widely differed, then the nucleation on the gain edge and gain corner will not vary much. And when it becomes very high, it's close to double, then what will happen? That means when theta is very high actually, then what will happen? Nucleation can happen anywhere. There is not much difference between boundary, edge and the corner possible. So that's the one important aspect which comes directly from this equation. Second important thing which I will discuss about is the nucleation on the dislocations. As you know, dislocations are present inside a crystal, that is inside a grain, and many times they actually help in nucleating certain phase. How does it do? Basically, dislocation has a distorted zone. Okay, dislocation has a distorted zone means there is a dislocation core, and the dislocation core actually helps us to nucleate. Why? Because dislocation core has a lot of distortion energy. If a new phase nucleates on that, the distortion energy can be relieved, and that's the reason we can gain actually, system can gain a lot of energy if it allows to nucleate some phase in the dislocation. Mathematically how it will look like is very simple, again not very difficult. Again we can actually consider such a kind of model, but we don't need to do much like that. It is much easy. What you need to know is the strain energy because of the dislocation, and that equation is available in the books, in the mechanical metallurgy books it's available. So what is done is that to delta G dislocation, okay, for heterogeneous nucleation, is nothing but, again pi r cube, this is a volume term, minus gc plus delta gc plus delta gs, that's basically the volume term, plus twice pi r gamma minus, this is basically your twice pi r square. This is basically your, because of the interfacial energy gamma between dislocation core, dislocation and this crystal, this is the energy gain, okay, remember. And what is the energy loss? Energy loss is basically related to W core energy of dislocation multiplied by AD is the surface area of this dislocation core log of R by R0 minus, sorry, R by R0 minus 1. This part is what is new. This is core, dislocation core energy. And this is basically because of the strain relieved surrounding areas, okay. And this equation is familiar to many of you if you have looked at any mechanical metallurgy book. So that is the total energy of the system. So therefore, if I do the analysis, that is if I make delta G by del R to be 0, I get R star. That's what R star is, basically a very complex equation. It's not a simple equation anymore. Gc plus Gs 1 minus alpha d. What do you see here? Basically you see two roots of this equation. This is no longer this will be equation related to R square, okay, that's the problem. And because of that, because log and other things are there, so this R star has two roots, one plus minus, this term will give you plus 1 root and minus 1 root, and alpha d is related to again all these equations, minus 2ad delta gc plus delta gs minus divided by pi r square, small r, okay. So that means what? That means I can actually have two sets of values of the this nucleation for nucleation, and this is what is shown here, okay. When alpha, if you consider as plus value, then A with situation will happen, that is delta G will reduce as a function, very monotonically will reduce, you see here monotonically getting reduced, and final value will be R star 2 star. But when it is basically minus, then you have situation like B, so it goes to a one minima then another. So therefore you have two different values of one R star, one here, another R star, one there, okay. So you can clearly see that when the B is there is one value there, another value there. When A is there is only one value. So that this has been seen actually, depending on the type of dislocation energies, and basically if alpha d is very small then doesn't matter, but alpha d is substantially high compared to the other parameters, then this becomes very strong, and in that case you can have two different values of R star. Actually what does it mean? It means that you can actually, one system can select two different R star, one small value, one high value. So you can have two sets of precipitates on dislocations when alpha d is very large. One will start with a bigger size, much bigger size, almost 3 times bigger than the other one, and then the size, there will be distribution of these different phases, these precipitates of different sizes. That's what people have seen actually. So mathematically one can actually show that it is possible. Basically what you need to do as a part of your home assignment is that you can take this equation and solve it, so that you can get R star, different values of R star. So you will get a equation in terms of r square, and solving that equation, basically it's a quadratic equation, so that solving the equation will give you 2 roots. Anyway, you do that. So that's basically for the nucleation. Only thing which I probably had to would have talked to that the nucleation rate, but nucleation rate for homogeneous heterogeneous equation will remain same. Only thing which will change if you consider the nucleation is that delta G star in the equation of homogeneous nucleation rate will be replaced by delta G star heterogeneous. That's the only difference. Everything else will remain same. F C0 will remain same. Exponential minus delta G star heterogeneous by divided by KT will be used in case of heterogeneous nucleation. So other than that, everything is going to remaining same. So I simply complete almost all the introductions of different things, although it looks like introduction, but it's quite a bit of it, phase transformation, because I have talked about thermodynamics, then I talked about diffusion, and then interfaces, and followed by nucleation, and I use different aspects it. Now it's become very easy for me to talk growth, because that is what is left, okay, growth of phases during phase transformations. What I am going to do is the next class onwards I am going to take solidification as the first thing, although I have talked about solidification quite a bit, but we will take about solidification morphologies, solidification and then followed by morphologies and what actually happens in the real cast structures. And then I will move on to the solid to solid phase transformations. There are many solid to solid phase transformations to be covered, so we will spend for each of them, depending on the type of phase transformations, we will spend about 2 to 3 lectures each and then complete.